Welcome to Infinita Lab podcast. Today, we are taking a deep dive into the future of aviation with Ben. He is advisor and chief of staff at DBT Aero. Um, DBT Aero is making some bold claims about revolutionizing aircraft, uh, its performance. While they are making something new, they will cut the fuel cost, and there are a bunch of other things. But fuel cost is one of the biggest thing, right? And how it is like how the airplanes are built. Is their design, as you can see behind Ben, is totally out of the Star Wars, Star Trek, right? So that is what I think very attracted me towards Ben. And they are talking about fuel cost, but also passenger and cargo and everything kind of goes with it, right? So Ben, it's great to have you here.
Oh, thank you. It's great to be here. I think I'm looking forward to the conversation. Very impressed with your background as well. I think it's great to speak to people that have a background, especially materials, which of course aircraft, you know, rely on very specialized materials. Weight's so critical. So I'm looking forward to the conversation.
So let's answer the elephant in the room. The first question. Okay. What is wrong with today's aircraft? They fly, they work. I don't understand where is the problem. But you
Well,
are saying that it is fundamentally inefficient, right?
yeah, well, first, there's only a few planes that'll actually carry an elephant, and we're not one of them. So no elephants in our plane. But yes, the current aircraft, it's not that there's anything wrong with them. They're very safe. They've been developed for the last 100 years, and the challenge is that it's easier to iterate a design
Hmm.
than it is to create something new. And it hasn't been for lack of trying. A lot of uh, I'm sure people have seen all kinds of versions of airplanes with wings in the front. And the challenge for aviation is now to say, is there an opportunity to take a next step?
Hmm.
What's the step change that provides a bunch of additional efficiency? And we think the box wing, which you see behind me, is a step change. It provides 30% overall efficiency gain. So it's quite dramatic. And the way that it manages airflow
Hmm.
is very different than the current system.
Hmm.
Now, the reason the current system has come about is because there's a lot of infrastructure around it. There's a lot of design, including the idea of certification. So you can't say there's anything really wrong with what we have. It's really just saying there is a next generation, just
Hmm.
like computers.
Hmm.
When the initial IBMs came out, there was nothing really wrong with them, but there was nothing to stop us from moving forward with better chips, better designs, portable computers. The first computers that I worked on were
Hmm.
room size. Now they're pocket size
Hmm.
with 10 times the power. So aviation is in that space, that opportunity right now. They just haven't
Hmm.
taken it.
Hmm. So that's where your double box tail design comes in, right? So that is I see that is the most prominent feature when I see all the plane. So what is so
Yeah,
special about it?
there's three elements that drive the efficiency overall.
Mm,
One is the box tail design. When you think of a winglet, when they
mm,
when they were working on aircraft originally, and airplanes went 60 miles an hour, there
mm,
there wasn't a big advantage to reducing the wingtip vertices of
mm,
a 60 mile an hour airplane.
mm,
Suddenly, when you get into jets and you're traveling at hundreds of miles an hour,
mm,
there became a real advantage to stopping the high pressure air under the wing from leaking into the low pressure space above the wing, and you lose lift and you create drag.
Mm,
So they put in winglets. Winglets are a 3% efficiency gain. If you fold the wing over and create a box,
mm,
you suddenly have this air flow and lift configuration that's a 30% gain, 10 times the efficiency gain of a
mm.
winglet. And
Wow.
it's the math works. The key elements are that the wing as a box is structurally stiff.
Mm,
So I don't know if you've done this. I love doing it. You always get a seat by the a window seat near the wing.
mm,
And in a big airplane, 747-400 flying across the Pacific, the wingtips start flying a couple of thousand feet earlier down the runway than the rest of the plane. And
mm,
if you look at a B-52, the wingtips travel 6 feet. Yeah, it's a long flex, and
mm.
all that flex is inefficient. You're
Oh,
losing efficiency by flexing the wing,
okay.
but you have to do it so it
Mm,
doesn't snap.
mm,
There's no choice.
mm,
So you lose some efficiency in the fact that your wing is very long and your structure has to be extremely light. So
mm,
you end up with a lot of flex, and flex is inefficient, and you're carrying this long structure out into the distance. We've designed the box tail
mm,
so that it's a shorter wing, very stiff. Because it's shorter, it's boxed, it's reconnected. You can see the
mm,
configuration is naturally structurally like an egg, naturally structurally stiff,
mm,
but it flies like an airplane with a much bigger wingspan. So it has all the benefits of a long wingspan and all the benefits of a short, stiff wingspan
mm,
packaged into one bundle. The other thing about it is, so you've got one is the overall, aerodynamic configuration of the wing,
mm,
but we're also building in a lifting body fuselage, so we're very efficient. And then we're looking at things like laminar flow, and laminar flow is a very tricky animal. When
mm,
you're working with the old style of aircraft, and you've got a propeller in the front
mm,
or a jet engine producing thrust that's slamming into and all the turbulence that comes off the wing that hits the tail.
mhm,
So you got a whole bunch of airplane after your thrust generators, and you got a whole bunch of airplane after you're dumping air off the wing.
mm,
And all that air coming off the wing, all that air coming out of your thrust generator, especially twin engine aircraft where the engines are on the wing, or
mm,
single engine aircraft where the engine's on the nose, even a
mm,
turboprop, there's
mm,
just a lot of turbulence. You just cannot get any kind of efficient, really efficient airflow. It's
mm,
just so disturbed when you get it. You'll see strakes and all kinds of things added to the plane to get the air to behave the way you want it. We, using our configuration, the air is clean until after it leaves the airplane,
mm,
right? Once, by the time we create turbulence, what little turbulence we have, it's past us. So it's not impacting aerodynamic surfaces. It's not impacting fuselages and
mm,
other parts of the plane. It's
mm,
clean all the way down.
mm,
So this laminar flow gives us a tremendous advantage, a lifting body fuselage. So these elements put together
mm.
give us a huge efficiency in airflow and noise, you know, and it also laid out a design that what we call propulsion agnostic.
Mm,
And I know you probably want to talk about propulsion later, but right now I'll just mention that we can hang, because it's a pusher,
mm,
we can hang a lot of different solutions onto the plane.
mm,
Where if you're a tractor, a puller, or hung on the wing, you've, you're fairly limited to what your
mm,
choices can be.
mm.
So that's how we get this efficiency, and that's the answer to the Boxtail question. It 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 wasn't obvious, and it took decades for what is it they say? It's a 20-year overnight success.
Yeah, I mean, it's you are kind of improving efficiencies everywhere. That is what I see. Uh,
Right. But some
and
of those efficiencies couldn't be done. I worked at Cessna, my beginning of my career, And when you've got an airframe that looks like that, and you have a propeller at the front, and you've got an air-cooled engine,
Mm,
right? And you're working with inexpensive, aluminum materials, and you there's only so much you can do to clean up the aerodynamics.
mm,
Yeah, there's just only so much you can do.
mm,
And we don't have some of those problems because the fundamental design is different.
mm. But still, I feel like, the way the aircraft companies are obsessed about cutting fuel cost and reducing emission is, and you are talking about like 50% fuel
Mhm.
reduction, right?
Yes, that's
Uh,
right.
my question to you is this, okay? The way they are so obsessed about these things, it is hard to believe that anyone has not done this before.
Well, yeah and no. I mean, the challenge when you're looking at our target is regional air transportation.
Hmm,
So that market now it has other capabilities, but right now we're saying we have a solution for regional air transportation
hmm,
that provides a dramatic, revolutionary change in the economics of servicing these areas. It's fast, it carries a good load over a long distance, and it's efficient. But the challenge is finding these solutions is
hmm,
not so easy. If when I worked, when I have spent a lot of years with the aerospace industry and various companies, it's hard to go back and say, we have this aircraft.
hmm,
Now we want to fundamentally redesign it from scratch, which is,
hmm,
a 4 or 5 year process. It
hmm,
took us more than a decade.
hmm,
So there's a long process, and we can't grandfather in anything with the certifying authority.
hmm,
So when a lot of aircraft companies, Piper, Cessna, Boeing, all these different companies go out there and build something, a huge amount of what they're building
hmm,
is certified based on the previous models and
hmm,
previous history and previous structures. It's really hard for somebody at a company to say, we're not going to worry about any of that.
hmm,
We're going to start from scratch and pay all the years, the time, and the cost to
hmm,
redevelop something when in their minds, they have a backlog, people are buying them, they're happy with them. Why should we make those changes?
hmm,
So they do tend to fiddle with the edges a lot more. But when you say that, from the outside, it does look very fiddle at the edges. But from the inside, when you're the engineer, the aerodynamics are changing. Aircraft are getting significantly more efficient,
hmm.
but not step change more efficient.
They,
And
they,
that's what we offer.
these are like small improvements. These are, and that is,
Yeah.
it goes with the risk averse. Like you are at the end of the day, you are flying people. They are off the
Well, at
ground.
the end of the day, you're answering to stockholders and
Hmm,
investors, and at the end of the day, you're flying people and responsible for an aerodynamic structure that's safe.
hmm.
And and that combination makes you, momentum driven. It's
There is a lot of
hard to,
inertia. Hmm,
yeah. There's a lot of it, and investors invest in things for a reason. And when you change your mission, they get upset.
hmm,
They think we're investing in Boeing because, well, you build these airliners that look like this and sell like this and fly like this. Now you're saying you're going to dramatically change the plane and spend an extra 10 years developing a new design. That's not what we invested in. If I wanted to invest in that, I'd have invested in a startup somewhere. And so the investors are resistant, the executives are resistant because of the way the bonuses work. The system works to kind of reject. And when you look at almost any other industry, Apple, any of these different industries, there's always a resistance to a big change until suddenly the big change is the norm.
I mean, it is good for startups though,
It's
because
good
big
for
companies
startup.
would not. That is how I think NVIDIA formed. Intel did not pay attention to that, gaming kind of chips.
Yeah, that's
So
right.
I also some of the things are pretty good. In Also kind of noticed that while you're making it, you are using 3D additive manufacturing. That is basically how you will kind of change how aircrafts are built. So could you tell a little bit about that? What's the deal there? You know.
Yeah. I can tell you a little bit about why we chose that. You, of course, have a deep expertise in material science. So
Mhm,
I'm a little bit careful that you're not going to call me out, but hopefully you'll be polite.
mhm,
I might oversimplify, but I do know you're an expert in the space, and that's we we have been talking to some very deep experts in material science and trying to understand all the intricacies. My understanding of material science, I'm a mechanical engineer. I have a background, a very superficial background in materials. So I understand that, the molecular structure of the material, the annealing qualities, the flexing qualities, the stiffness, the brittleness, all these things are really important. And I can still do a little bit of the math around that. But when you're talking about additive manufacturing, and I've done a little bit of work in that space, it's very tricky and you need the real experts to look at it. But we think when we start getting into it, and we've talked to people that do this and already make component parts in 3D manufacturing, they've done additive manufacturing for component parts, mostly non-structural,
mhm,
but parts the same. And so they're building up an experience set, and the FAA and other certifying bodies are starting to build up an experience set around the materials they're comfortable with. So if you introduce a new material, you've added years to your certification process. But if I can say, well, it's the same material, it's just built up a little differently. Instead of machining off the excess parts, we're building it up from scratch and we're still annealing it. We're still going to do these processes you're used to. We can still test it. But we think there's a huge advantage. And those advantages, one are we can build significant subassemblies
mhm,
with additive manufacturing and then have bigger pieces to snap together. We
mhm,
can still have good maintenance characteristics. So I was specialized and wrote a white paper, a deep research paper on composites manufacturing. And I spent a lot of time working in composite shops. Composites had a huge advantage because you could build up a pretty significant subassembly in a composite and
mhm,
then stick it in an autoclave, and you had basically a finished part,
mhm,
very strong and exceptionally light.
mhm,
And so it had these great characteristics. The downside was you had to have a very expensive kit of equipment to make composite parts. You
mhm,
had to have layup tools and you had to have a mold that was perfect. You had to put it in a very expensive, basically oven and autoclave and cook it under pressure using inert gas. There was all complexity to making composite parts to get the outcome. And then you had maintenance issues. If
mhm,
you break the thing in the field, it's hard to fix it and be sure that the repair meets the original design requirements.
mhm,
It's really hard to do, especially if you can't remove the part from the airplane and run it through sonic testing and ultrasound and X-ray. Very hard. With additive manufacturing, there's an opportunity to fix a broken part even on the aircraft, and be sure that it meets the original design criteria. So not only can I make a major assembly, not only can I confirm that major assembly meets my design requirements and then simplify my assembly process, but I can also repair the thing. And that has some real benefits to us. Then on top of all that, because we're a laminar flow aircraft, we don't have rivet heads everywhere. We
mhm,
don't have countersunk screws. We don't have to deal with the properties of aluminum overlap, right? I mean, I built, aluminum airplanes for a while, for a long time, and everything's rivets. And when
mhm,
you've got a high load, in certain parts of the wing, it's almost, they're half a diameter apart. So you
Hmm.
got a lot of rivets. And laminar flow is sensitive to that sort of thing. Getting that boundary layer right along the wing to behave the way you want means you have to be able to create an air surface, the wing shape, and the surface shape exactly the way you want it. And you don't want it flexing. You
Hmm.
don't want stuff sticking out of it if you can help it. All those things create aerodynamic resistance. Everything you can get rid of. Additive manufacturing fixes basically all that. We get that for free, and we still get major components built as one piece. We still get the ability to basically pre-assemble components of the aircraft and put them together on the assembly line without having to do piece by piece, sheet by sheet aluminum riveting,
Hmm.
you
Wow.
know. So there's
Hmm.
a lot of really good stuff. And if we have it right and the science says we do, they're very strong, right? And you can create the material characteristics you want. So not so brittle that it cracks, not so soft that it flaps around on you.
Hmm.
And we can do it both in the shape, so using an egg, using the shape, and the materials itself, to get the property we want exactly. I guess somebody once said you got to make the perfect martini. You have to control all the ingredients, and that's where we're at.
Wow. I earlier when we had a discussion, I think you mentioned about you guys built the whole UAV, right? Unmanned aerial vehicle using 3D printing, right?
Hmm. Yeah, we did,
Yeah. Uh, so it,
but that it was a test. It was a proof of concept. Turned out to be very straightforward.
mm,
It is a proof of concept, so it doesn't have a lot of load capacity, but it
mm,
did prove that we could do it. Now, the beauty of the drone what we call subscales, right? Not five-seater or a nine-seater commuter aircraft, is that there are a fair number of additive manufacturing equipment around that can make the whole thing in one go.
mm,
Just build up the plane almost maybe three pieces kind of thing, or
mm,
four. Very small part count when you're dealing with small pieces of equipment. Now, I've seen additive manufacturing make a house, but this is different.
mm,
They don't have a bed. They bring in basically a crane and they slowly build up. And it takes them a couple of weeks of unmanned house assembly, and they sit there and additive manufacture a home. Very impressive.
mm,
We're not looking at that. But we are looking at the idea that you can get shapes you can't get any other way, and
mm.
you can do it with this additive manufacturing system, in a minimum number of components. So I think, does that help you with that question? I think it does give us an opportunity to do things that we want to take up, and it gives our operators, the people that buy our planes and fly them, a pretty significant advantage in operating cost.
Yeah, totally. I think I keep hearing, you know, and I keep wondering actually. So I forgot the name of the company that built the whole rocket using additive, right?
Oh,
Building.
yeah.
What is the name of the company, right? And they are not only building but actually launching these rockets.
Hmm.
So, that has a huge impact on the, makeability, how fast you can make, but, obviously how efficient you can make the technology wise, what kind of surfaces you have. And also the cost, is just huge, huge. I mean, in mass production, that would be sort of, another level for things that are not produced in millions, especially like, right? So that is something which I pretty impressed, and I am very kind of, as a material scientist, I'm kind of, want to see that more and happy that you guys are actually doing that. So I want to ask that in the context of laminar flow. I think you talked
Hmm.
about it earlier. But laminar flow, I don't
Hmm.
know what it is, but laminar flow is the holy grail of efficiency, right? And
Hmm.
you ask any aviation geek, and they would talk about it. Keeping airflow smooth across a plane surface is insanely difficult. If I talk about like, common people language, layman language, it is very difficult. And that is where laminar flow comes in. So, and you talk about that a lot in terms of DBT Aero. How did you
Hmm.
solve this problem?
Well, I won't go into too much detail on that, but the challenge about managing airflow in
Hmm.
general is to look at the aircraft as a whole.
Mm-hmm.
And that is where we came from. What historically, you look at an airplane in chunks. It's, well, the engine guys have decided on this propulsion system, and here's the propeller that makes that work, and we need this much horsepower, and then we got to cool it, so we have a cowling, and then we have, so they end up with a lot of pieces, and then they try and optimize the
Hmm.
individual pieces, and then they try and create an airplane. It's tricky. The airplane itself, the configuration might have started as a very high level sketch, but as you get down into the details, but we tried to keep that holistic view all the way through the design. So we were very conscious that anything that sticks into the airflow is going to create less efficiency.
Hmm.
And so the box tail, there is a box wing, this is the box tail. The box tail offered more efficiency. The flying body, lifting body, fuselage offered more efficiency. The whole design around the aircraft was really saying, if we stay at a high level, if we stay at the big picture and drive the design, then we can get all these different efficiencies. And especially because the inventor, the original inventor, wasn't part of the sort of aerospace community. He hadn't worked at Boeing for 30 years. He wasn't kind of stuck in a mindset that said, this is the way airplanes look. And well, if I tweak this or tweak that, I can get a little extra.
Hmm.
He did a huge amount of research and he said, wow, if you look at the way this works,
Hmm.
um, you know, I think I can get a whole bunch of more efficient out of it if I don't bother doing it the way they're doing it.
Hmm.
Certainly not the first time that's happened. Even in aviation, it's not the first time it happened. I mean, you look at supersonic flight and the Concorde and other aircraft, even though it doesn't look that way, the Concorde is revolutionary. The F-16 fighter is revolutionary. There's a whole bunch about the aerodynamics
Hmm.
that they that made that had to be implemented to get the performance they want.
Hmm.
But they're subtle. But we think now in our design, we looked at it from a much bigger picture and said, well, what if we make all these change? What if we don't start from here and iterate? What if
Hmm.
we take a big blank piece of paper, look at the math, and
Hmm.
figure out what pieces give us the best performance and how to put them together to get it? That's
Hmm.
how the engine ended up in the back. That's how the propulsion ended up in the back. That's why the tail is a box, the box tail. That's why we're not putting all kinds of flaps and spoilers on.
Hmm.
We don't need them, and they mess up our airflow. But everybody else says, well, how are you gonna do it if you don't have all kinds of moving parts on your wing? Because we have a different wing.
Hmm. I mean, it is a bit surprising for me, by the way, what you said, that planes are not looked holistically, right? And the flow. I thought that it is like, once they make it, they have these wind tunnels, right?
They
And
do. Oh, they do. But then
but
they're
hmm.
so they'll start with a design. I mean, they generally start with the design they have. They imagine in their mind, if you're building a 747 and you've never built a two-deck aircraft before, you're still looking at a swept wing, mid body. You're looking at a tail. You kind of start there, so nice and big, and you swoop, and then you say, well, we're going to put a deck up here. So we got to get the aerodynamics to make it work. And then we put block versions of it into wind tunnels just to see if it'll fly, you
Hmm.
know. and make sure the math is right on the wing. And they'll often modify which aerodynamic, what the wing cross section will be. They'll start with one wing cross section, and they might try two or three others. And then they'll look at the length, they'll look at the tail design. Then they got to work with the engine manufacturer to get the thrust that they want. So,
It's a
they do.
top down kind of thing. They first make whatever they want, and then they kind of, make efficient later. What you are saying is kind of bottoms up. That first we will think about what would actually give a flow, and then basically, okay,
Yeah.
got.
What if we're not constrained? What if we don't think about a wing being straight out and having a tail that's separate?
Hmm,
And, Burt Rutan, and there's people in front of us, and we're standing on the shoulders of those people who have spent, their life messing around with
hmm,
various configurations. And we're another version of messing around with various configurations. But we found one that we think has tremendous commercial benefits
oh,
that's very unique to this design. It happens to bundle up a group of benefits that work very well together
hmm,
and would service the regional market extremely well. So
awesome.
that's where we are. It makes a great five-passenger aircraft. So
Hmm,
for general aviation, it's a very scalable design. Some things don't scale so well. This one does. So it means we can make a five-seat version, a nine-seat version, a 19-seat version, and maybe in the future some others. So there's a lot of opportunity given the design scalability.
hmm,
Again, it's got to do with the box tail and the stiffness. We don't have the same problem that, when they started getting bigger and bigger jets, you
hmm,
started to have to figure out how to keep the wings from dragging on the ground.
hmm,
You know, how do you how do you make a 777
hmm,
with a wingspan that big? And you have to have the wingspan because you got to lift the weight and you want to fly at 30,000 feet. So you got to have a whole bunch of lift. And then you got to have a height to get it off the ground to the engine to fit up. So
hmm.
you end up in this sort of series of trade-offs to get where you want to go. And the box tail gives us some significant advantages around stiffness, but also acts like a much bigger wingspan.
That's impressive. At least where you are, the plan is pretty impressive. You also have some, things about production efficiencies, right?
Mm.
In a big way, you want to improve that. So, airplanes take years to build, right? And so, what could you tell about that? What are you?
We think we think that if we focus on our aerodynamics and our manufacturability at the same time, that
Hmm,
we can get a lot of benefits. Aircraft have been built in a very similar way for a very long time. And again, it's momentum. This is the way we build them. And when composites came along, it took a long time for the aircraft industry to kind of adopt composites. And even now, they've only partially adopted them. Yeah, there's a lot of components that are composite, but they really haven't. They love composites for non-structural parts of the plane because you can get the shapes you want, but it's still pretty expensive to do.
hmm,
We're thinking if we adopt additive manufacturing, and we purposely tested it on one of our proof of concepts, we can get exactly the shape we want. We can have much larger subassemblies as single piece,
hmm,
which reduce the cost,
hmm,
and we can reduce the cost of assembly because we have fewer pieces to assemble. So, and it reduces the cost of tooling, it reduces the cost of jigs and fixtures, it reduces the cost even of training. The workers don't have to be as skilled across as wide a range of things um, if the components are bigger and they're more a minimum amount of assembly is required on major components instead of one sheet at a time and thousands of rivets.
hmm,
So there's some real upside there. But the question about manufacturability is very important because if it's an incredible, when you look at some of these aircraft that have incredible performance
Mm.
numbers. You look at things like the SR-71 and these, super high altitude, super fast
Mm.
aircraft, even the shuttle,
Mm-hmm.
but they're near impossible to assemble. I mean,
Yeah.
it was a huge job putting the thing together. So you just can't afford to make very many, and maintaining them is difficult
Yep.
because they're complex. And so we know for the regional carriers that we're expecting to buy this thing, both freight and passenger, they're not going to spend, 500, $600 million on an aircraft that carries 9 people.
Mm.
You just can't do that. So you have to keep looking at the design of the aircraft itself so it's efficient to operate. And you have to look at how you make it so it's efficient to build and efficient to purchase because they still have to pay off the capital. So we do think that additive manufacturing is going to be a big advantage to us. We also think that partnering with experts is a big advantage. So finding these companies that are very, very good at certain
Mm.
types of manufacturing, additive manufacturing, wire harnesses, other things, even the control system is going to be optimized. It's not likely to be the old, cable system that you would find on a Cessna 172, you
Mm.
know, because it doesn't lend itself to the efficiencies we're looking for in assembly.
So,
So,
so it is basically a lot of simplification.
well,
Simplification
it's
of
appropriate application of technology
mm.
to get an optimized design that gives us a performance characteristic that we want with an assembly and manufacturing characteristic that we want. And you have to puzzle together all those technologies. So it's not really simplified, it's optimized because the
Optimized.
materials, just like you would know, just the material science alone is complex. We have
Mm.
to get the materials right, or the additive manufacturing doesn't help us.
True. True. Optimized.
Yeah.
And
Mm.
basically said, and which is, I think, you guys are the best position to actually do, because you do
We
not
think so.
have the constraint that Boeing has, which
Yeah.
is which
Well,
is
we
great.
don't. Well, and to be fair, Boeing doesn't make regional jet,
Yeah,
really doesn't. I mean,
that is true. True.
people are applying 737s into regional routes, the small versions, but we're looking at lighter routes than that. We're talking the 20 seat, 60 seat or less market, few hundred, hundreds of miles, not thousands of miles. We're not crossing oceans.
Yeah.
And that space is you look at the people that have all tried to build planes for that space, it's
Mm.
hard. It's
Mm.
really hard because you have to, there's just so little margin for error in terms of financial profitability. It's just hard to play in that game.
Mm. I mean, regulation comes in there as well.
Hmm.
FAA is very strict,
Mm.
very strict, right? So,
Yeah, the regulating authorities are funny about taking risks with passengers' lives. They don't they don't like it, You have to be sure. And you have to not just be sure. You have to prove that what you're telling them is correct.
yep.
So it's trust and verify at the extreme.
Hmm. So how are you? So it is like, a lot of certification, right? It is a lot of so how are you navigating that?
We are already talking to certification authorities. We're talking to some partners that are experts at helping companies through the certification process. We expect to engage much more fully um, as we get into production very early.
Mm.
To some extent, when you talk about Boeing and Cessna and some of these other aircraft manufacturers, they have a
Mm.
huge advantage because they already have all those relationships.
Mm.
In fact, in some cases, the certifying authorities have offices in their headquarters building.
Mm,
There's a partnership, there's a data flow that's established. The certifying authorities already know what to look for in the design because it looks like designs that they've been looking at.
mm-hmm,
We're building those relationships, but part of the challenge is going to be they're going to be learning to some extent as fast as we are because they're looking at a different wing, a box tail, and we're saying we're going to do it with additive manufacturing,
mm,
not just we have to test the material and prove that its characteristics meet the requirements. They have to come up with sort of a way to write the certification
mm.
that follows the rules but certifies something they've never done before. That's interesting.
That would be interesting, and also I think it is some steep learning curve for them too.
It was funny. I'm a pilot, but one of my instructors, coaches, pilot flying coaches, the woman was one of the few people in her country that had a license to see was a designated um, pilot license issue, right? Designated what they call designated authority. She could issue pilot's licenses.
Mm,
She could issue a pilot's license to someone or certify someone to fly a plane that has never been flown.
wow. Mhm,
You have to be right up at the edge of expert to do that. They authorize this woman to basically get in a plane that's never flown,
mm,
fly it, and then license other people to fly it, which means, and when you talk to her, she really could look at planes, get in them, and understand what was tricky about them.
mm,
Okay, you don't want to stall this aircraft because it
mm,
won't recover. You got to be very careful in ground effect. You have to watch out for this. You have to. She could learn those things fast enough to not die,
mm,
and that was a pretty good trick.
mm,
And we have the same challenge with the FAA. We're going to be working with the certifying authorities, and in some cases, they're looking at a plane that doesn't look like any other plane, and they
mm,
have to work out how they're going to certify it. And we want to be as close to that, make sure they have all the data they need. One of the reasons we're looking at building these prototype, like these drones or smaller aircraft, is if we fly around a light design for thousands of hours at a small scale with nobody on it, we have all this data
mm,
that we can turn over and say, look at the way it performed. And we've tested all these materials after 10,000 hours. And
mm,
here's how they're behaving. And
mm,
here's what's going and they can say, yeah, okay, I see how you're handling the flow of stress through the wing root. It's
mm,
not cracking, it's not failing. It turns out to be a lower load than we would have anticipated.
mm,
Okay, we understand how we can certify that. You
mm.
know, that is going to be key. That's going to be, and this is why some people don't do it. It's hard.
Mm. But that is interesting. The example you gave, like it is like somebody has the feel for it, kind of almost has a feel, sort of very good feel that oh, this is like I have seen people have who have the same kind of feel for cars, for example. That oh, there is something wrong with it. They touch the car and they can kind of feel that where the problem.
Yeah.
You know,
Yeah. The
so.
race cars, when you talk about Indy and Le Mans and Formula One, these drivers can tell right away
Mm,
if the car is behaving the way it's supposed to. And
mm,
they might do one lap and they might not get over 60 miles an hour. And they'll come back into the pit going, yeah, no, it's not
mm,
right. Do it again. Something's wrong. Because
yeah.
they sure as heck don't want to find out something's wrong at 180 miles an hour in an S curve.
Mm.
That's a bad combination.
And probably FAA has
They
these
do.
kind of folks who can not only look at the data but also can kind of have a feel. And for them, it is a different design does not matter. What matters is kind of what their gut tells them about this thing.
Mm,
Mm,
Well, their instincts will point them to areas where they would probably want to do a deep dive.
mm,
They can't deep dive everywhere,
mm,
but they can look at something and say, "Ooh, that wing root looks like an awful lot of load.
mm,
How are you going to survive that? How are you carrying the load through the wing root across the fuselage. Where is it cracking? Where is my stress? What are you doing with but when you look at it and you think back, the first jets had square windows because the certifying authorities didn't realize the stress cracks when you pressurize and depressurize over and
mm,
over again were a problem.
mm,
It just it never came up before, you
mhm,
know. So they missed it. And so the comet had a problem. They would fly out over the ocean and disappear. And no one knew why until they realized that the 90-degree corners on the windows were causing stress cracks. And it also created the need for stringers in a certain design that stopped cracking from propagating and causing an entire aircraft to fail. So if you
mm,
did get a crack, it could only travel a certain distance and it couldn't cause the entire structure to fail. So they learned a lot over the years. And, the expertise in these certifying authorities is,
mm,
they'll have an instinct for where to dig deep.
mm,
Well, that looks tricky.
mm,
Let's talk about that. Where's your evidence of that? Let's
mm.
test that. They don't get everything, but when you look at the history of aviation, they do a pretty darn good job.
Yeah, they have to. I mean, and then so so this is exciting. It is ambitious, pretty ambitious. There are multiple things.
Hmm.
The field itself is ambitious. So my question is, where are you right now, and what is next for you guys?
We're we've proved our concept. We know it works, and now we're positioning ourselves to move into production and certification.
Mm,
And that's where we're going. And we're engaging with possible customers to understand and make sure we understand exactly how it would fit and where the savings are. And we've done a
mm,
fair amount of financial modeling, and we think the savings to an operator is extremely significant.
mhm,
And we think that it could allow several orders, right? So the aircraft itself is efficient.
mm,
That's great, right? I saved money 50%,
mhm,
but it has some second order capabilities. Like I could rejig my network
mm,
to service more cities out
mhm,
of fewer hubs. Wow, that's a big cost saving, especially if you're a freight carrier. Can I do more? Can I optimize my network? Does this give me an ability? When you think about um, certain air routes over history,
mhm.
there are whole airports that were built as refueling stops,
Yep.
in the Pacific, right? You wanted to get somewhere, but you couldn't get there, so you had to stop and refuel. Well, when the 747 rolled out and suddenly you could go nonstop between these cities, that
Mm,
that that made a big change in ticketing and passenger carry. There was a fairly significant route network impact, second order impact. Um, and then there's even third order impacts that say things like, well, if um, if I can create an aircraft that has certain flight characteristics,
mhm,
that I can service new cities that I couldn't service before. I can do new things that I couldn't do before in a way I couldn't do them, um, and and I can do them in a way that's cost effective enough so that someone could afford to use that service,
mm,
right? So when you look at phones,
mm.
um, some of the things phones do now they could have done 40 or 50 years ago if you had the odd $100 million in a building big enough to put the computer.
Yep. Mm,
Sure, you could have done it on an IBM mainframe,
mm,
but when you shrink it down to fit in your pocket, it's a completely different market, right? And
mm,
even Apple often says, we're excited to see what you're going to do with this capability because we
mm,
can't think of everything. They create a capability, put it in the hands of the consumer, and the consumer goes nuts.
mm,
Suddenly it's a gaming platform. Or, and they're shooting movies on it. That wasn't what they were thinking when they built it. We think it has the same opportunity. It has some tremendous environmental opportunities because we're propulsion agnostic. It
mm,
means that it's one of the few airframes you're going to find
mm,
that has an aerodynamic efficiency that allows us to move forward with propulsion technology, not resist propulsion changes because there's only so much you can do with my airframe.
Mm,
There's only if I have to put the engine in the front, there's only so much I can do.
mm,
But if I'm in a position where I can say, okay, I can start with a piston style engine, I can move to a hybrid of some form.
mm,
I can move to hydrogen hybrid. I can
mm,
move to battery electric. I can just
mm,
keep going. And the stiff wings give us a place to put things that other airframes don't have.
mm,
It's not all that clever to put really large groups of batteries in flexy floppy wings.
mm,
The batteries don't like it. And generally speaking, it has some pretty poor outcomes when you bend them back and forth over a period of time.
mm,
It doesn't go well. We don't have that problem. So we have capabilities. We think there's at least the primary benefits, a second order of benefits, and a third order of benefits that roll out of this design. And so that's what we think we're going to next. We're trying to deliver those to operators so they can achieve these benefits. So the public can move freight more effectively, people can travel. There's a whole series of rural communities that survive by their air service, and right now that air service is kind of failing them. But we think the air service could enhance them, do the opposite if you had the right solution. And that's where we're going.
This is amazing. This is amazing. I'm pretty sure about it. One very interesting thing you said about, I made this, like, you were giving the example of iPhone, that this is made and then, the market actually, you have some idea of market, you start with some market, but then market application actually find the way, use cases find the way. And very big example is Nvidia made GPUs for gaming, and then
Yeah.
they were found like this is very valuable now, right? It is found application in AI. So I feel the same way. The way aircrafts are right now, or airplanes are right now, they are kind of boring and and not available. Sort of, I kind of still have to go um, and this can change. This can change if it has the right kind of efficiency, right kind of fuel profile. There are so many airports. Every big airport has accompanied by like five different small airports. Small airport everywhere in US. So rural communities and other things are, I think, a big. So good luck. I feel that it has probably a kind of bigger market than anybody is thinking about.
We
Uh,
hope so. We know we've explored what we see. But yeah, we're hoping that people are going to look at it and think I can do some things with that you didn't think of. And we'd be happy to partner with them and talk about them. We know we've already been approached by people that wanted to do some interesting things we hadn't thought of.
mm,
And we're our airframe and our performance, the combination of range, speed, fuel efficiency, noise, right? We're quiet. We're very quiet. Is something they said, well, if all those things, with all those characteristics, we can actually do this thing that we couldn't do before.
mm,
And so, yeah, I agree. I think you're right on there.
mm,
There's people are going to take what we do and decide to do something we hadn't thought of
mm.
because the characteristics were the engineering dynamics that we're giving them create an opportunity that didn't exist.
Totally, totally. So Ben, this has been an awesome conversation. I think DBT Aero is breaking barriers, unlocking opportunities in the aviation sector. Frankly, I can't wait to see where you guys go next.
Well,
Uh,
thank
thanks
you.
for thanks for coming on the show.
Well, thank you for having me. It's been a pleasure talking to you.